Welcome to part two of our analog inferencing series. In part one, Sagence's Rich Terrill walked us through his company's technologies, so I recommend you check that out if you haven't already. In this video, we'll wrap up our conversation with some questions I have based on what was presented. So you're doing an 8-bit quantization of the weights versus an almost infinite continuum of floating point that somebody like NVIDIA can do. What sort of fidelity concerns are there in terms of the overall result when you wind up with quantizing 8 bits versus using floating point type of solution?
What we find is that most of the applications today are quantizing to 8-bit in digital already because of the weight cost to store all of that. And you don't get a tremendous amount. You do have much more dynamic range, if you will, and precision within that range. But in a typical application, if you take a vision application like recognizing if someone's about to leave a store, and these are just relative numbers, they're not absolute. If floating point 32, the golden standard, is 93% accurate, int 8 may be 90% accurate, we may be 88. You only need 70% for the business model. So almost all these applications today are already being quantized before deployment, after the training. So when we take it, it's fairly straightforward. Many of the applications now, people are looking at going into int 5 and int 4 to further try and save the cost of the memory to store it.
And then there's some sort of database or something that your software plugs into in order to transpose it into your fabric. Is that the way it works?
Exactly. So they would train typically with FP32, get to the accuracy that they wish, then they would convert it using the same tools, often the CUDA tools from NVIDIA, into int 8. And then that int 8 would be, I show it in a can here, this trained network. We import that directly. It would be not directly, it's exported through ONNX or PyTorch. We import that and use that as the baseline. So we don't intrude on the training process, because what we want to be able to do is to take out the existing hardware and plug ours in and run to the same test data. And so by using that same trained network basis allows us to do that.
You're obviously implementing this on silicon. What's your current prototype matrix size? And where do you see it going per chiplet, if you will, and as far as the overall size of the inferencing matrix that you're building?
So we have product chips. So we're not announcing the product here, but they're in our lab and we'll be announcing them early next year. Our first chip has hundreds of millions of weights, and they're arranged in a tiling approach that allows us to allocate them not arbitrarily, but optimally to whatever network or networks, because we can run multiple concurrently. So if you look at a vision network, for example, that may be 5 to 50 million weights. So we can run multiple networks concurrently. Something I didn't say in the talk, but it's pretty important. Our hardware is statically scheduled. So when we compile, compiler's probably a misnomer. What we're really doing is a place and route problem, because we know exactly how many weights and what the connectivity is in our chip. We can do more like an FPGA, do that binding to the physical object during the compile time, so that at runtime, we don't have any of that runtime complexity of scheduling and resource management. And so what we have in the lab, in our product chip, it's hundreds of millions of weights. So we're able to implement extremely large networks or multiple networks.
So there's a network above or under a network of programmable connectivity of these individual flash cells, or are the flash cells what you're talking about?
It's both. So there is a programmable data path through the whole chip. So it's an array of the multiple arrays of these flash cells that have a programmable connectivity of how they feed one to the other. And then between each of the arrays of flash cells, there's a custom SIMD engine, which does the interlayer processing. So if you look at a classic neural network, a CNN or a DNN, there's a layer of processing. There's some digital compute of activation, pooling, pruning, quantization, ReLU, CLU, things like that, best done in a CPU approach that then feeds back into the vector matrix multiply for the further reduction of the data into metadata. and ultimately to the classification of the objects that are found. So that's all done, but it's all fully programmable. We don't have any hardwired paths, if you will, and that gives us flexibility to implement a range of different networks and applications.
Okay, so you use, going back to your diagram with the D to A and the A to D stuff. So you use the D to A to program the subthreshold change, I guess, on the gate of the flash cell, right?
Kind of. So when we program it at boot time, we use charge circuitry that actually programs with the voltages, not part of the operating. It's like a supervisory mode. So we have to program and load up those floating gates with the right charge. Then when we
Right.
run it, that's when we put the activation data goes to the control gate, not the floating gate as shown there.
Right, because the weight is built, it is built into the floating gate.
Correct. And there's
Yeah.
a lot, and you would, I'll predict your question. There's, this is a 1,000 tall column of weights. You could saturate that op amp at the bottom very quickly. So this is all scaled so that we're able to get it's operating in the nonlinear region of the transistor. So that's part of the trick, is to be able to get digital data out of that and then not saturate it because you're running it at such a high level that you then have to scale it down. It's scaled during that quantization process from the compiler.
So there has to be some kind of normalization at the output of that sense amp or op amp, then I would guess.
It's a mix. It's done during the compile, it's done in these cells, and it's done in the circuitry. So it's a multi-level approach.
Okay, and then it's no secret that flash cells wear out and you're hammering these things fairly hard, I would think, with different weights. So is there a wear mechanism problem with this architecture?
The flash cells do have a wear mechanism, although it's extraordinarily high now. When I started with E squared memory, 10,000 was the limit. Now it's millions, but we don't actually program it that frequently. We program it at runtime, and then it stays there. And so we're not designed to do high switch out fungible applications where you're changing on a microsecond basis. It would just take too long for us to program. It wouldn't be tractable. So we don't really have any issues with wear out because we don't program that frequently. We get nowhere near the event horizon for any sort of an oxide failure wear out.
So it would not be applicable for inferencing or something like search. It's more of a static application, like you said, image recognition, that kind of thing.
With something like an LLM, you put everything in, you put billions of cells in, and then the search, you have a pseudo fungibility because everything's already in there. And then it just becomes, where does the token get directed during that process? And so we wouldn't, an application would not be suitable if it had to change, 20 times a second. That would not be good for this. But most of the applications we see are fairly static in a reasonable time frame.
So what kind of programming, let's say per day or per hour or whatever, would a typical application see in this?
In Vision, it would be per week or per month. It doesn't change that often. So if you had, say, for example, defect detection and anomaly detection in manufacturing, once it's trained, you want that to run, and then you may update it if you identify some new boundary conditions. That's weekly, monthly. That's not that frequent. The vision with recognizing bad actors might be more frequent. If you found some person of interest, that might be hourly, but we don't see applications that go down below that. And even that would be pretty rare. And then in the LLM side of it, those don't get retrained or don't get reprogrammed very often because the training part of that is such an extraordinarily expensive and complicated task. And they just don't want to do it unless they have to. It takes months, weeks to get it done right. That wouldn't be reprogrammed much at all.
So one of the big problems that we're seeing right now is all this talk about 3 Mile Island being turned on and just crazy amounts of power going into data centers to support AI. You're claiming you have 1/20th of the power, so you're no longer 700 megawatt like they are worth of electricity use. You're down around 35 or 40. Is that where you're going with all this?
That's exactly where we're going, and doing it in a way that is scalable, so that we can keep pace with whichever way the networks go if they get smaller or larger. By doing the more natural way of doing the computing, you get this substantial savings, but a lot of times those sort of savings often trade off one against the other, We're saying we're doing them at the same time.
In other words, you're including all the necessary processors and any other kind of support you need around your chip. It's not just the chip itself, saying it's doing a minor function as opposed to a system level power burn, if you will, to do the whole solution.
Yeah, this is system level. We've put most of the processing into this module. So that main digital processor there is doing the 5% of the math and the 100% of the traffic cop stuff. The host, of course, the CPU and the server will also be then, because, something like this thing here, if we do the math, this is actually 80 of our PCIe cards versus 944 of the H100s. There is routing that's going between them, and the host is doing that. But we simplify that problem too, because all the weights are resident. They don't have to be fetched from anywhere and then loaded up and moved around. So this is a system level power assessment that we take from the NVIDIA numbers, the DGX boxes to do that, and then our comparables.
The main digital processor is a third-party thing, as is the HBM3 memory. Is that true?
This is an over-the-horizon project. This is something we're working on right now. We've spec'd out what that processor has to do. If there's a standard off-the-shelf one that will do that, we would elect that. If not, then we'll go design that or design that in partnership. It largely is doing traffic management between the modules that you see here. And so our favor is to use something that exists if it's there. And if not, we know exactly what needs to go into it, so we could design that.
And what's your vision in terms of the size of the matrix one of these modules can do?
This would be, because it's modular at the board level, we would just put in more boards as necessary. So this 70 billion LLM, the Llama 2, this is taking 80 of our boards. It's hierarchical, of course, but because they're statically scheduled, the master program knows where everything is. It doesn't have to figure out where it's been put into some sort of dynamic system, so it's simpler. And so we don't see an upper limit of that scaling, because the data flows through in a very hierarchical fashion within the card as much as possible, and then card to card in a server, and then server to server is required.
So who builds a server? Is that you guys, or do you have customers for that?
Or
that will be off the shelf. Those will be partners. So we've been working for several years developing relationships with server vendors, systems integrators, and ISV software vendors in anticipation of this. So when we go and engage customers, we often are accompanied by server vendors or software guys that are doing the analytics and the applications, because it's really a cooperative engagement to do that.
Now, do you have design interest or design wins? May I ask that much?
So for this product is still proposed, but we have substantial interest in it. The sort of interest saying, okay, I see how you do that. I get this analog stuff. I see your power savings. If you can do this, we're going to test drive it. And if it does what you claim, we're going to integrate it. So we've got that for a variety of different products that we'll be announcing early next year. But we've been working with customers for some time, starting with our software and then into the assessment of their networks. And now we've got multiple customers who are ready to adopt first products and integrate it into their systems.
Okay, so putting on my marketing hat, there are other people doing compute and memory. What's your differentiator?
A few things. So we have done it at scale. Several of them are fairly modest. And so you really need to have a lot more compute capability. And that means scale. That means, tens, hundreds of millions of weights to do complex and multiple networks concurrently. If we divide it into two camps, you have non-volatile and volatile. In the non-volatile side, doing it in the deep subthreshold, that's a big win for us. So if you're using the full VT range of the transistor, then you're paying a power penalty. You're still at an advantage, but you've not taken all you can out of the system for that. And so that's a big one. The other one is that analog or non-volatile cells have a natural drift mechanism over time. That's unavoidable. Just the physical aspects of reading and writing to it, as well as any sort of environmental things such as thermal excursions, that changes the programmed voltage. And that's something that we understand extremely well because we've been working with this type of technology literally for decades. And so understanding that and being able to predict it and then design and mitigation features and capabilities, that's essential. So of all the non-volatile statically programmed, that's a critical element that needs to be fully solved because it needs to be transparent to the end user. Any sort of update or refresh or retuning, that's all going to be background stuff. And that's exactly what we've done. So it's non-intrusive to the operating of the system. On the volatile side, there's SRAM and DRAM, of course, and there are advantages there and flexibility. Disadvantage being the multi-level storage, because as these networks grow larger in size, you're still going to have an awful lot of memory, and you have to manage that. So our advantage of having multi-bit per cell, deep subthreshold for the extremely low power dissipation, a deep understanding of all of the mechanisms of error and drift and how to mitigate it. And then finally, and it's a little bit of philosophy, we understand stochasticism extremely deeply. And a neural network is naturally stochastic. There are naturally errors that arise in any sort of a synaptic structure, and they tend to cancel each other out. And we take full advantage of that because we have very large implementations. They cancel themselves out in large measure. So taken together, all of those are significant and we believe essential. We do say though, and emphasize compute in memory or in-memory computing. That's how it's going to be done in the future. It's just the right way to do this. And it's not just for AI, it's for a broad class of problems that are being noodled on today in the universities. There's going to be several people that are doing it. It's that big and that important. And we're fans and supporters of all of them because we really want this to come to bear on the problem.
Yeah, you're preaching to the choir. I actually started an analog computing series in my blog. I've been only with electronic design since April, but that was one of the first things that I lifted in for the readers to catch up on because analog does have the power savings. And you guys are doing the implementation of the next generation of the old K2W stuff. So there is a sweet spot in Foundry nodes as far as your technology goes. In other words, if you take it down to 3 nanometers, is the leakage so excessive it's not practical? In other words, there's no gains in going to a finer resolution lithography, or like I said, is there a sweet spot for you, or does it actually continue to scale like digital does?
And the flash cell, so we're on a 40 nanometer process node, and that's the most advanced you can get the embedded flash that we use. It's going to go to 22 or 28. There are limits to that because of the programming circuitry and the oxides to do flash. It's not like SRAM. You just don't keep shrinking with metal and channel length. So we'll take whatever the most advanced node is, but by taking on this, we're showing a heterogeneous mix of processes. So you can see on there the mezzanine die at 7 nanometer. We don't need to go smaller because we don't need to go faster. And in fact, going smaller, you'd start to get a problem because you'd have this tiny little mezzanine die and this whacking big stack of analog die on top of it. So we have similar sorts of interests as other folks doing this, although different topological constraints to that. So by being able to mix and match, we're able to take full advantage of what's out there. What's essential is we're not driven to the 3 nanometers or 2 or 1.8 or whatever's after that to get performance. We're not in our compute. We're doing 95% of the compute is up here in this analog slice. You don't run that very fast at all. You're taking advantage of the law of large numbers and doing it in parallel. And importantly, doing it completely predictably. Our latency is set and definitive and doesn't change. It doesn't matter what the programming is or the data. You always get the same exact time through there. We don't rely on super fast clocks. We rely on analog in-memory computing.
That makes sense in terms of power supplies. What sort of supplies are you using? You said 40 nanometers, but I'm sure there's some of our power supply manufacturers and designers that would be interested in knowing where that's going for compute in memory sorts of chips.
Yeah, it's multi-level, I believe. And with the product announcement, we'll have more on it. I think there are 4 voltage rails. They're not very high. Just like a flash device, a flash chip has multi-voltage rails, and all the charge pump circuitry manages off the high voltage rail that goes into it. So we don't do anything extraordinary or extreme. At the outside, our chip, it's a digital chip. That's the key thing. So this is the chip here on the lower right. There's no analog outputs on it. It's all digital. So it looks like a digital chip to the outside world.
And then in terms of rollout, give us a little bit of an idea of timing. You said your stuff is on the bench now. Sort of major milestones and stuff that you can share with us as far as that goes. When is this thing going to hit the pavement? And then I can start doing my Picasso paintings on this thing.
Well, it's next year. That's a really wide window, of course. But one of the things that we wanted to do and that we held true and fast to is we've got to get it working completely before we show it, because there's enough, crossed arms. Is this really going to work? Skepticism about this whole in-memory compute and then analog in-memory compute. We're going to have it completely working when we show it, and we're well down that path. So we can't wait to tell you much more about the details of it, but we're showing you a product here, a board. So it exists and people have seen it, and we're getting the final fit and finish done on it. And just as soon as we can tell you about it, we can't wait to. But yeah, our emphasis, our focus today, of course, is on the technology. And of course, you have readers who want to get their mitts on it. And believe me, I can't wait to help them get their mitts on it. But we want to make sure that it's a delightful experience when they do that and it doesn't feel like a science project.
Lovely. We're running low on time, so I'll leave it to you to do any kind of wrap-up comments that or missed points that I didn't ask questions about.
That difference between static and dynamically scheduled, that's really the core problem. And if you solve the dynamic problem better and better and better, you probably can never get to good enough. You really have to look at it differently. And that's what the in-memory compute gives you. And we've elected the flash fabric to do that. So that's kind of one of those, I think, for your readers, kind of interesting looks at it, how it's actually being done, and then ultimately the business care abouts and attributes that come from it.